And the Newton algorithm implements Newton's method in order to find the root of an equation. And so we start off with the iterate being 1. The reason why we want to limit the number of iterations, we don't, if it's not going to converge, we need to at least say if you haven't converged by 100 iterations, then you need to print out something that says it didn't converge. Okay. Then we have an initial guess for where we think our root is. So let's say our problem looks like this, and our curve goes through like that. And then this is 2, and this is 4, and this is 6, and this is 8. We might guess our root to x0, we could guess to be 5. We don't know exactly what it is, but we know it's between 4 and 6, so I would guess 5. Okay, so we would give it an initial guess. We need to give it an epsilon tolerance. That means how many decimals or how close do we want this to be? So we need to decide on what that epsilon tolerance is. And then we also need an epsilon, which I called epsilon 1, that gives an idea of what's close to 0. So if you want your 0 to be maybe 10 to the minus 10, then that's what you would define for your epsilon 1. And Imax, as I said, is the number of iterations allowed. I usually let it be somewhere around maybe 25 or 50, because Newton's method converges very quickly. So you shouldn't have to have it do 100 iterations. The only time we would do that many iterations is if it does have a place that the derivative is close to 0, but not actually too close to 0. Okay, so we were just getting started. So the first thing we'll do is compute the derivative of f and evaluate it at x prime. And if the absolute value of f prime of x0 is less than epsilon, we can exit. Okay, we'll exit the code. Okay, so then the next step is to compute x1. So x1 is our next iterate, and it's x0 minus f of x0 over f prime of x0. So now that we know x1, now we want to check to see number 4, how close are they? So if the absolute value of x1 minus x0 is less than epsilon, then the root is equal to x1. We'll print that out and then we'll exit. So far we've had 2 ways to exit the code. That is, if the derivative is 0, we're going to quit because we know it's not going to converge. And we should say it, make a statement here that says, so you need to print out a statement. So in here, print a statement that tells you why it quit, because otherwise you won't know why it quit. So print a statement saying something like f prime of x0 is equal to or near 0. So then here, you also want to now print a statement saying f of x is equal to 0 for x equal to what you just found. Okay, so now if that hasn't happened, then we're going to go another step and we're going to determine our next iterate. Okay, so if the iterate that we just looked at is bigger than I max, so if iterate, so now we have iter is bigger than I max. That means we've already gotten to beyond where we were supposed to go. Then we're going to exit. And here now you're going to print a statement. Saying that you reach the maximum number of iterations. Okay. If that hasn't happened, so if none of those things haven't happened, then we're just going to keep going. So now we're going to increase the number, the iterate. So iter is then going to be iter plus 1. Okay. And then we're also going to let x naught be x1. So now this redefines our starting point. And then basically we'll return to step 2. So that is how, that's the whole algorithm. Okay, the question is, again, how do you find x naught? Well, you can graph it and get a general idea, or just use the intermediate value theorem. That is, find a value where the function is positive, find a value where the function is negative, and then you know you must have a root, provided the function is continuous, you know you have a root inside that interval. So we can always rely on the theory of the problem. Okay, so let's talk about the rate of convergence. So for the rate of convergence, we want to consider star. I'm trying to figure out what I said. Where what did I call star? I started something, but I don't see it. Oh, there it is. Okay. So we're going to consider the Taylor series approximation. And so for the Taylor series, we had f of xn plus 1 equal f of xn plus f prime of xn times xn plus 1 minus xn plus f double prime at some value cn over 2 factorial times xn plus 1 minus xn squared. Okay. Yes. All right, so let's consider that. So again, our hope is that what we are trying to find, that our xn is actually our root. So we're going to consider this for our root alpha to actually be xn plus 1, or our next guess. Okay, so if that's the case, then we have 0 is equal to f of xn plus f prime of xn times alpha minus xn plus f double prime, and this is at some cn divided by 2 times alpha minus xn squared. Okay, so now we already defined, so let's just solve for alpha minus xn. Okay, so when I solve for alpha minus xn, which is right here, so I solve for alpha minus xn, I'm going to get minus f of xn divided by f prime of xn. And then I'm going to get minus alpha minus xn squared. And then this is going to be over 2. And then I'm going to get f double prime of cn divided by f prime of xn. All right, so now we know alpha minus xn is just the error in at en plus 1. Okay, so en plus 1 is just the absolute value of alpha minus xn, but assuming alpha is xn plus 1, that's the error. So we're going to plow through the above equation with absolute values. So we're going to get the absolute value. I'm going to get f double prime of cn divided by f prime, 2 times f prime at xn. And this is times the absolute value of alpha minus xn squared. And then, so it's going to be less than or equal to that. And that term is equal to the absolute value of f double prime of cn over 2 f prime of xn, and this is times en squared. Okay, so that gives us that en plus 1 is less than or equal to some number c times en squared. And here our c is this value. So c is the value in front here. So that's going to be the absolute value of f double prime of cn divided by 2 times f prime at xn. So that's c. All right. So c is the maximum, the biggest that that thing can be. All right. So this thing is going to be c. So in fact, we're going to let c equal the max over all x in the interval. The interval is between a and b. of the absolute value f double prime at x. And then if I want it as big as possible, I'm going to divide by the minimum of all x in the interval of f prime of x. All right, so now we get quadratic convergence. If you remember, the bisection method had linear convergence. So this is a quadratic. So what are the advantages of this method? So the advantages well, the main advantage is that it's quadratic convergence. It converges faster. So you will see when it's going to converge, it converges very quickly. But the disadvantage, and that is it may not converge. So this thing is not guaranteed to converge. And that's because it can hit a place where the derivative is close to zero, and that will send it in a divergent thing. Okay, and we need to know the derivative of the function. Okay, so those are the disadvantages.
Excuse me, Dr. Locke, can
Yes.
you go up a little bit? So for here, the 1, 2, 3, 4, 5, the fifth line, the alpha, is that we write the en plus 1 equals to the absolute value of alpha minus xn?
Yes, I think I left out a step. Let me check here. So if we want that alpha, and that's xn plus 1, I can let me go back a minute. Let me see. Did I leave out a step? I left out a step. This is actually, okay, so I see what I did. Alpha is the root. Okay, so here, let me go back. Oh, that's not where I want it. Oh, that is right. Okay, I left out a step, that's all. The step I left out is right here. Okay, so then this becomes alpha minus xn plus 1 plus xn plus 1 minus xn is equal to negative f of xn over f prime of xn minus alpha minus xn squared over 2 times f double prime of cn over f prime of xn. Okay, so now en plus 1 is alpha minus xn plus 1. It's the error in at the xn plus 1 iterate. Okay, so therefore, now these two, this is equal to that. So that drops out. The way we define xn plus 1 is xn minus. So those two are equal. So they drop out of the equation. I just left that step out. So I shouldn't have put alpha equals xn plus 1. I should have just put alpha is the actual root. Okay. Does that make sense now, Yibing? Yibing,
Yes.
does it make sense now?
Yes.
Okay. All right. Thank you. Kayla probably was a little confused too, because I just skipped that line. Okay. All right. Okay. So we have a theorem. All right. So the theorem is let P of X be a polynomial of degree n greater than or equal to 2 with real coefficients period. If all the roots alpha I, where you have alpha 1 is bigger than or equal to, so now we're going to order them, alpha 2 bigger than or equal to, all the way down to alpha n. What in the world? That is not bigger than or equal to. I need greater than or equal to. Let's redo this. Greater than or equal to, greater than or equal to, greater than or equal to the last one, so that we can order all the roots of P of X are real. Then Newton's method yields a convergent strictly decreasing sequence. XK for any initial value X naught greater than alpha 1. Okay, so you can find these one at a time, and then you end up with this sequence. Now, this is where life gets a little difficult, and that is because in the undergraduate course, I would not prove this theorem, but in the graduate course, I would prove this theorem, and I have one of each of you. And so I don't want the graduate student to be cheated out of the proof. So I'm going to do the proof, and my undergraduate student, don't be too stressed. Okay. Proof. Okay, so let's, without loss of generality, let's assume that P of X naught, this is the polynomial, is greater than 0. Okay, now we know that if it's greater than 0, okay, it's not going to change sign until before we get to the first root. Okay, so since P of X does not change sign for any X bigger than the first root. Okay, so we're assuming that we have some polynomial whatever it looks like. And we're going to, so if we start off with P naught, so let's say is positive, it's not going to change sign until, I think I'm going the wrong direction. If it's positive, it doesn't change sign until it gets to the first root. So we have that P of X is equal to I don't know why I did it this way in my notes, because this is crazy, but I'm afraid if I change my notes, let me see. Can I change my notes? I think I can change my notes. We'll see what happens. I'm going to go ahead and try. I don't like to change my notes in the middle, but the way this is defined is crazy. A naught xn plus a n minus 1 x to the n minus 1 all the way down to a1x plus a naught. Okay, this is greater than 0 for x bigger than alpha 1. And therefore, a sub n is positive. Okay, so now the derivative P prime of X has n minus 1 real zeros. And I'm going to call them beta I with the fact that alpha 1 is going to be bigger than or equal to beta 1, which is bigger than or equal to alpha 2, which is bigger than or equal to beta 2, because they are occurring in between, which is bigger than or equal to all the way down to beta n minus 1, which is bigger than or equal to alpha n by Rolle's theorem. So now you see why I did a little bit of that stuff in the beginning of the course, just so you would have some idea of what these theorems actually do. So since P prime of X is degree n minus 1, and that is definitely bigger than or equal to 1, these are all of its roots. And P prime of 0, no, P prime of X is greater than 0 for X bigger than or equal to beta 1, because AN is positive. All righty, so let's apply Rolle's theorem again. So now applying Rolle's theorem again, and recalling that n is greater than or equal to 2, where do we get that from? We get that from here, that n minus 1 was bigger than or equal to 1, so n is greater than or equal to 2. We obtain P prime of X is greater than 0 for X bigger than beta 1, bigger than beta 1. And then P double prime of X is greater than or equal to 0 for X bigger than or equal to beta 1. So it says, thus, I'm gonna call this star. Why do I have a, so thus P and P prime are convex functions for X bigger than or equal to beta 1. Okay, so now let's get into actually using Newton's method. All right, so now we have this. So now we have that xk is bigger than alpha 1 implies that's the first root, that xk plus 1, which is equal to x and xk minus p of xk divided by P prime of xk. Well, both of these are positive. Remember, both of these are positive. So therefore, that number is less than xk, since P prime of xk is greater than 0, and P of xk is greater than 0. So from our double star, oh, so xk plus 1 is bigger than xk. So therefore, xk plus 1 is bigger than alpha 1. Okay. So from double star above, we get xk is bigger than alpha 1, which is bigger than or equal to beta 1. And by Taylor's theorem, we conclude this is what we get. 0 is equal to P of alpha 1. That's the first root. But that's P of xk minus alpha 1 minus xk times P prime of xk plus, we're going to get alpha 1 minus xk squared, and that thing is over 2, times f double prime of some cn, I'm sorry, not fp, that's p double prime of some cn, and that thing is greater than P of xk. This thing is positive, okay? Second derivative is positive, it's concave. We also know that it's convex, I apologize. So we have alpha 1 minus alpha k over 2. So therefore, this is greater than this, and this should be a plus, plus alpha 1 minus xk times P prime of xk. All right, here alpha 1 is the between C, this C is between the two things, the iterate and the first root. Thus, we now get, oh, skip a line. So P of xk is equal to P prime of xk times xk times alpha 1, no, Okay, wait a minute, I gotta get it right. P of xk is equal to P prime of xk. This has to be xk minus xk plus 1. And this holds by the definition of xk plus 1. Okay. Thus, we get 0 is greater than P prime of xk times xk minus xk plus 1, and then plus alpha minus xk. So notice how I put xk in there, but that's just equal to P prime of xk times alpha 1 minus xk plus 1. And xk plus 1 is going to be bigger than alpha 1. Follows since P prime of xk is greater than 0. Okay, that's a heavy duty proof. I want you to take a look at it, think about it for a moment, and then we can do questions on that. Now, before I go on to the secant method, I want to say something about the homework. So let's see. Okay, so secant method. All right, so the secant method is similar to Newton's method, and that's why we do it next. And I actually do this slightly out of order than your book does it, but it's okay. All right, so the secant method, so we're going to now assume we have 2 estimates. So the secant method requires 2 guesses. All right, so we're going to assume that x0 and x1 are 2 initial estimates of the root alpha. All right, so we want to approximate the graph of f of x of y equals f of x by the secant line determined by the 2 initial points x0 and f of x0 and y1 x1 f of x1. Okay, so now I have something that looks like this. So it's slightly different. Okay, so here's my curve. All right, and obviously here's my root. And I have some point x naught and another guess x1, okay? And so now I'm going to draw a line between them, the secant line between them. So when I draw the secant line between them, as you can see, I get a guess where it crosses the axis. So that would be my point x2. That would be my next guess. All right. So this point right here is the point x naught, f of x naught. And this point right here is x1, f at x1. All right. So now what is the slope of the secant line? So the slope of the secant line is easy to find. That's just a change in y over the change in x. All right. So for us, the slope of the secant line is simply f of x1 minus f at x0, x naught, divided by x1 minus x naught. Now, if you remember what we did before, we said, let's just suppose that that next iterate x2 is exactly what we want, our guess. So now let's suppose that this x2 is, we just happen to get it the first way. Well, x2 is also on the same line. So therefore, we get that the f of x1 minus f of x naught divided by x1 minus x naught is f of x1 minus f of x2 divided by x1 minus x2. Okay, because the slope of the line is the slope of the line. But we want f of x2 to be 0. So I'm going to chop that off. So now I get x1 minus x2 is going to equal f of x naught. Well, let's put x1 minus x naught first, times f of x1. And then I'm going to divide by f of x1 minus f of x naught. So then we can clearly see that x2 becomes x equals x1 minus this quantity, x1 minus x naught times f at x1 divided by f of x1 minus f of x naught. And so in general, our next iterate xn plus 1 is going to be xn minus xn minus xn minus 1 times f at xn divided by f at xn minus f at xn minus 1. And so this is the derivation of the secant method. Okay. All right, so let's look at the secant algorithm. All righty. So for the secant algorithm, we're going to do similar what we did before. We need to set iter equal to 1. We also have to choose two guesses, x0 and x1, and they have to be distinct clearly. Then we're going to set an epsilon. That's going to be our tolerance. And we also need to define Imax equal to the maximum number of iterations. Okay. Second step. We now are going to calculate x2. Equal to x1 minus x1 minus x0 or x0 f of x1 divided by f of x1 minus f of x0. Okay, so now we'll check if the absolute value of x2 minus x1 is less than our epsilon tolerance, then the root is equal to x2, and we exit. And we will print, as I said before, this is what we found. Next step. Now we're going to increment the iterate. So we're going to go, and if iter is greater than Imax, that means we've done all the ones we were supposed to do. Let's quit. I was only supposed to do 50. I just did, I'm up that, I'm done. So now if that hasn't happened, we're going to let iter equal iter plus 1. And now we have to shift. So we're going to let x0 be x1, and then let x1 be x2. And it must be done in that order. And then we will return to step 2. Okay, so that is the algorithm. We will do convergence of this thing tomorrow. No, we won't. We'll do it on Thursday. And talk about the advantages and disadvantages of this method. And then we will do some fixed point methods. Okay.